Good morning, ladies and gentlemen. My name is Jan Freisky, and today, on behalf of my team, I'll present a paper on design of a layout-friendly EDT decompressor. Our presentation follows a pretty standard flow. I'll start with a short background introduction of a decompressor, which is a key component of any compression scheme, and here we'll focus on EDT decompressor. The core of the presentation is on the segmented decompressor. I'll also show some experimental results to illustrate that the segmentation improves layout without sacrificing the quality of compression. As some of you may remember, we introduced embedded deterministic test in an ITC 2002 paper. And actually, 1 year earlier, we introduced the first commercial test compression product based on the EDT technology. We expected that test compression would become a pillar of DFT methodology going forward for decades. So even though the basic compression technology was capable of achieving 2 orders of magnitude compression from the very beginning, a number of significant enhancements were developed over the years to keep up with growing design sizes and new types of patterns to accommodate new fault models such as transition and cellular test. And as to be expected, the process of improvement of adding enhancements will continue as long as technology is in use. This picture shows a pretty generic architecture of compression. It has a decompressor controlled by a small number of inputs and driving a large number of scan chains. On the output, we have a compactor which compacts the responses from the scan chains to a very small number of outputs. Over the last 3 decades of research and development, a large number of different decompressors were researched and even implemented in commercial tools, starting with very simple ones like Illinois scan, through combinational decompressors, all the way to sequential decompressors with continuous flow receding. It is now widely recognized that the latter offer the highest encoding capacity and efficiency. The other advantage is that they can perform hybrid function as decompressors of deterministic patterns and pseudo-random pattern generators in logic BIST. A sequential decompressor has 2 parts: linear feedback shift register and a phase shifter. In EDT, we use a ring generator as PRPG. It is faster than both the Fibonacci and Galois-based PRPG because there is at most 1 2-input XOR gate between any flip-flops, and all feedback is local. It is also more modular, and it can be easily segmented and distributed. The injectors, through XOR gates, provide the compressed stimuli. The phase shifter distributes decompressed stimuli to a large number of scan chains. Each output of the phase shifter is controlled by a 3-input XOR gate driven by 3 different flip-flops. Its role is to drive a large number of scan chains while minimizing linear dependencies between its output streams. This way, a high encoding capacity and efficiency is achieved with reduced area overhead. Once the architecture of the decompressor is defined, meaning once we have the injectors, the polynomial, and phase shifter, then for each scan cell we can create an equation in terms of input variables. When an ATPG tool produces a test cube, as shown in red in this figure, we don't fill the remaining positions with random values, but rather we form a system of linear equations based on these specified positions. If this system can be solved, we have a compressed test pattern. Just like this one. When we apply the compressed stimuli through the decompressor, we obtain the original values of the test cube. In addition, the other positions, which originally were don't cares, are now filled with values that are implied by the solver. They serve as random fill. In this particular case, a very simple one, we succeeded in solving the system of linear equations. Our ability to solve those equations for a given distribution of specified values and the number of inputs depends on the architecture of the decompressor, which defines those equations. There has been a lot of work done by my team to develop algorithms for design of very efficient decompressors. In particular, how to select appropriate polynomial, where to put the injectors, how to configure the phase shifter to achieve the highest encoding capacity with the smallest amount of hardware, etc., etc. This research has been published extensively over the years. Let's take a look at the phase shifter using the decompressor shown here on this picture. The phase shifter drives 1,545 scan chains. Since every XOR gate driving a scan chain taps 3 flip-flops, the 32 flip-flops have to provide 3 times 1,545 taps, which is 145 taps per flip-flop. One monolithic massive circuit like this may lead to routing congestion, as can be seen on the layout picture. The green triangles represent EDT logic. So this is clearly not the way to go. The phase shifter has to be segmented, and we have been doing it for a long time. But this is the first time when we are presenting the synthesis algorithm behind it. In the development of the algorithms, we wanted to make sure that while targeting reduction of routing congestion, the encoding efficiency of the segmented decompressor remains very close to the single monolithic one. This is the overall architecture of a segmented decompressor. As you can see, we still are using one ring generator to allow flow of information between the segments. A ring generator is naturally segmentable. Each segment of a ring generator is connected to its neighbor, but just 2 wires. Here, however, each segment has its own phase shifter, which is driven only by the local flip-flops. Although this architecture with enough segments solves the routing congestions, it would be significantly lower encoding efficiency. In every cycle, each segment receives data from its input channel. In addition, segments 1 and 4 get 1 bit of information from its neighbors. Segments 2 and 3 get 2 bits because each one of them has 2 neighbors. So, for example, if for a given test pattern, all specified positions in scan chains driven by segment 1, the segment will be receiving an equivalent of only 2 free variables every cycle, one from its input channel and another from segment 2. So even though 4 bits are delivered to the whole decompressor every cycle, half of the bandwidth is lost to the phase shifter in segment 1 and 4. The maximum capacity available to segment 2 and 3 is a little bit better, but is still reduced to 3. The distribution of input channels to the segments and location of the injector XOR gates is the key to the efficiency of the decompressor, and this is also the main problem solved in this paper. The input channels inject data into ring generator through XOR gates, called injectors. The effectiveness of the three variables injected from input channels to segment depends where they are injected and how many cycles they remain in the segment before they leave it. The longer they stay, the more equation they contribute to. And by this, they increase the probability of successfully solving the equations and consequently contributing to improved encoding capacity. Here, for example, any variable injected in the to the input of flip-flop 13 leaves the segment in 2 cycles. On the other hand, variables injected to input of flip-flop 17 travel through 6 flip-flops before leaving the segment. The process of determining the location of injectors involves a number of steps. We start by selecting the size of the decompressor and its polynomial based on the number of input channels and the total number of scan chains. We have published a partial library of primitive polynomials in JETA in 2003, and it has one polynomial of weight 5, 7, and 9 for every degree from 9 to 660. So if you're interested, you can check it out. Subsequently, we divide the ring generator into segments. Typically, one segment drives not more than 500 scan chains, could be less. We also identify the possible places for injectors, making sure that they are separated by at least 2 flip-flops. They should not coincide with the XOR gates for the feedback taps of the ring generators neither. Then, for each injector, we compute its lifespan in its segments and build a 2D map of ordered injectors by their lifespan within each segment. The last step involves the assignment of injectors to input channels. The lifespan of an injector is defined as the number of cycles a variable injected at this injector remains within its segment. As it can be seen in this picture, a variable injected at the input of flip-flop 12 leaves the segment after just 1 cycle, so its lifespan is 1. On the other hand, a variable injected to the input of flip-flop 19 leaves the segment after 8 cycles. To maintain a balance between the overall capacity of ring generator and the complexity of the phase shifter, we only use locations separated by 2 flip-flops. In this particular case, we use only 4 best locations, starting with 19 and therefore skipping 18, then including 18, and so on. Using the same principle, we identify all eligible locations with the longest lifespan for all segments. Then we order them, putting the ones with the longest lifespan on top. Notice that the boundary segments 1 and 4, because they have the U-turns, the feedback, the loop, the U-turns, have longer lifespan than internal segments 2 and 3. This analysis helps us to create 2-dimensional map. Within each segment, injectors ordered by their lifespan with the longest on top. Using this map, we assign injectors to input channels, trying to ensure good encoding capacity of the decompressor. We achieve this by 2 objectives. First, each segment should receive the same or similar number of different input channels. Second, each channel should have a collection of injectors with a good mix of lifespans from long to short and anything in between. In order to achieve for each channel, in order to achieve this for each channel, we start with the highest available lifespan and move to the next segment while lowering the row and lifespan. We pick the injectors moving diagonally through the table, which actually should be considered as a barrel. We continue the process until each channel reaches its target number of injectors. Let's consider an example with 4 input channels and 4 injectors. Let's start with channel 1 and segment 1. We assign the best injector located in the first row. This is 19. Then we move to segment 2, represented by the second column, and we pick from one row lower, meaning row 2, with injector 23, and we continue with injector 5, row 3, segment 3, and end with injector 29 and the last row of segment 4. Similarly, we continue with input channel 2, starting from the best injector, injector 11, in segment 2, and after traversing segment 3 and 4, we come back to finish in segment 1 using the idea of modulo or a concept of a barrel. This process is repeated for input 3 using the same principle. And 4. In this case, the number of input channels was the same as the number of segments, and the total number of injectors was a multiple of the number of input channels. Each channel received the same number of injectors, but this is not a general case. If the number of injectors is not a multiple of number of input channels, we can still use the same algorithm, the same approach, but the number of injectors will not be the same for all input channels. In this case, with 3 channels, 4 segments, and 16 injectors, we cannot guarantee equal distribution. Channel 1 gets 6 injectors, while channels 2 and 3 get 5 each. Not the same, but close. In this case, we have 5 channels, 4 segments, and 16 injectors. Again, we cannot guarantee equal distribution. Channel 1 gets 4 injectors, while channels 2, 3, 4, and 5 get 3 each. Again, not the same, but close. For our experiments, we took 9 blocks that range in size from 2 to 17 million gates. Each of them has more than 1,000 scan chains. The biggest has 6,000 scan chains. And as you can see, the compression ratios range from 170 to 438. We can see that on average, the new proposed layout-friendly segmented decompressor has pretty similar coverage. The difference is here 0.01%, but it reduces parent count, interestingly enough, by 5%. This is actually pretty good, considering that the segmented phase shifter only uses its local flip-flops, as opposed to the monolithic one that uses globally all the flip-flops. On average, the proposed new decompressor has also 1.9x reduction on the overcongested edges and 1.35 reduction of the worst overcongestion number. An example of layout for design D9 is illustrated in Figure 8, where the locations of EDT segment cells is highlighted in the layout. This design has over 3,000 scan chains, so using 500 scan chains per module, it actually requires 7 segments, each driving at most 500 scan chains. It is clearly visible that the proposed decompressor is more spread through the layout instead of clustered in the center, which leads to less congestion in the layout when compared to the single decompressor. In conclusion, we propose the new layout-friendly segmented decompressor. We also propose algorithms to select the injectors, the key contribution of this paper, that are based on accumulated lifespan of each injector and balance on each channel. Since the input channels are distributed to the segments, the new decompressor has compatible performance, coverage, and pattern count to single monolithic decompressor. Finally, there is a significant improvement in key layout matrix. 2x reduction of the overflow edges and 1.35 reduction of the worst overflow number. This concludes my presentation. Thank you very much. Thank you.